Welcome to this problem walkthrough. Today, we're tackling a fascinating algorithm challenge titled Minimize Malware Spread 2. This problem focuses on optimizing the removal of infected nodes to minimize damage in a network. Stick around to learn about the approaches, trade-offs, and insights for solving it effectively. Let's dive in. In this problem, we are dealing with a network of nodes represented by an adjacency matrix. Each node is connected to other nodes directly or indirectly. The matrix is binary, where a value of 1 indicates a direct connection between two nodes, and a value of 0 means no connection. The nodes are labeled from 0 to N1. Now, some nodes in this network are initially infected with malware, and this infection spreads to all directly connected nodes. It continues to propagate through the network unless we intervene. To stop the spread, you are allowed to remove exactly one node from the network. The objective is to choose this node in such a way that the final number of infected nodes is minimized. If there are multiple nodes that achieve the same result, you must return the smallest node index. The input to the problem includes the adjacency matrix, which represents the structure of the network, and the list of initially infected nodes. The output is the index of the node you should remove to minimize the spread of malware. Let's look at some examples to better understand the problem. In the first example, the graph is a 3x3 matrix where nodes 0 and 1 are directly connected, but node 2 is isolated in a separate component. The initially infected nodes are 0 and 1. If you remove node 0, the connection between nodes 0 and 1 is severed, and node 2 remains unaffected as it is in a separate component. This leaves only node 1 infected, which is the minimal spread we can achieve. Therefore, the optimal node to remove in this case is node 0. In the second example, the graph consists of 3 nodes where each node is in its own separate component. The initially infected nodes are 0 and 2. Since no nodes are connected, the spread of malware is limited to the initially infected nodes themselves. Removing either node 0 or node 2 will leave only one infected node. However, since we are required to return the smallest node index in case of ties, node 0 is the optimal choice to remove. Now, consider the third example where all 3 nodes are part of a fully connected graph. Nodes 1 and 2 are initially infected. If we remove node 1, it disconnects from the graph, and node 2 will remain infected but will not spread the malware further. Removing node 2 instead would result in a similar outcome, but node 1 has the smaller index. Therefore, the optimal solution is to remove node 1, as it minimizes the spread of malware while respecting the tie-breaking rule. The problem also comes with some constraints and edge cases to consider. The graph is always symmetric, meaning the connection between two nodes is bidirectional. Each node is connected to itself, and all integers in the initial list are distinct. Key edge cases include disconnected components, where removing a node from one component does not affect others. If there is only one initially infected node, simply removing it will stop the spread entirely. For highly connected graphs, removing any single node will only isolate that node while the rest remain infected. Finally, if multiple nodes yield the same minimized spread, the smallest index must be chosen. Additionally, you need to account for the possibility of malware spreading through multiple paths, ensuring that removing a node effectively breaks these connections. To tackle the problem of minimizing malware spread, one straightforward approach we could consider is brute force. Here, we simulate the removal of each infected node one by one. After removing a node, we recalculate the connected components of the graph using the remaining nodes. The goal is to measure the size of the largest connected component that remains uninfected and determine which node's removal minimizes the spread of malware the most. If there's a tie, we choose the node with the smallest index. While this method is simple and intuitive, it has significant computational overhead. The time complexity grows cubically with the number of nodes, n cubed, because we need to calculate the connected components repeatedly for each infected node. Additionally, it requires n squared space for storing the adjacency matrix. This makes the brute force approach unsuitable for large graphs, even though it provides a clear picture of the impact of removing each node individually. A more efficient strategy involves leveraging the union find algorithm to optimize the way we handle connected components. Union find, also known as disjoint set union, allows us to pre-compute the connected components of the graph efficiently. Once these components are established, we can analyze the contribution of each infected node by determining how many nodes in its component are affected by malware. The node whose removal has the highest impact can then be identified as the optimal choice. This method is more scalable than brute force because the union find setup runs in O(n)(, and analyzing the components takes only O(n). Additionally, it has a smaller space footprint, requiring just O(n) for the parent and rank arrays. However, implementing union find requires attention to details like path compression and union by rank to ensure efficiency. Despite these requirements, its scalability and systematic nature make it a strong candidate for solving this problem. Another approach is to use graph traversal techniques like breadth-first search, BFS, or depth-first search, DFS, to dynamically calculate connected components. Here, for each infected node, we simulate its removal and traverse the graph to measure the impact on malware spread. This approach avoids the overhead of pre-computing components, as the graph is traversed dynamically for each infected node. However, this comes with its own trade-offs. The time complexity remains O(n)(, due to adjacency matrix traversal, and the space complexity is O(n) for tracking visited nodes. While this method is conceptually simpler and avoids the additional data structures required by union find, it can be less structured and slower since it involves repeated graph traversals for each node. This makes it less efficient for larger graphs compared to the union find approach. Among these approaches, the union find method stands out as the chosen strategy. Its balance between efficiency and clarity makes it well suited for this problem, especially when dealing with larger graphs. By pre-computing connected components, we minimize redundant computations, which is a significant advantage over the brute force method. Union find structures the problem efficiently, ensuring that the graph's connectivity is represented in a systematic way, reducing the likelihood of implementation errors compared to dynamic methods like BFS or DFS. Key observations supporting this choice include the importance of understanding the graph's connected components, the role of infected nodes within these components, and how isolating uninfected nodes determines the impact of a node's removal. The real insight here is that union find simplifies the problem by decoupling the graph structure from the infection analysis, making it the optimal choice for scalability and maintainability. Each approach comes with its own trade-offs. While BFS and DFS are conceptually straightforward, they lack the scalability and structure provided by union find. On the other hand, the brute force approach, though intuitive, is computationally prohibitive for large graphs due to its extensive calculations. Ultimately, the union find approach strikes the best balance between efficiency and maintainability, making it the most suitable solution for minimizing malware spread. By leveraging its systematic handling of connected components and avoiding redundant computations, we achieve a method that is both practical and scalable, ensuring a robust solution to this challenging problem. In this problem, we are tasked with minimizing the spread of malware in a network represented as an undirected graph. The nodes in this graph can represent computers, and the edges represent connections between them. Some nodes are initially infected with malware, and our goal is to determine which single infected node to remove so that the size of the largest connected component of infected nodes is minimized. To approach this, we can start with a brute force method. First, we need to understand the graph structure. The graph can be represented using an adjacency matrix or list, where each node is connected to others via edges, and a subset of nodes is initially infected. Removing one infected node impacts the graph structure by altering the connections and the way malware spreads. The next step is to iterate through each node in the list of initially infected nodes. For each node, we temporarily remove it by eliminating all edges associated with it, effectively isolating that node from the graph. This sets the stage for recalculating how the malware spreads across the modified graph. After removing an infected node, the next step is to recalculate the connected components in the graph. A connected component is a group of nodes such that there is a path between any two nodes within the group. To identify these components, we can use traversal algorithms like depth-first search, DFS, or breadth-first search, BFS. Once we've determined the connected components, we measure the spread of the malware by counting the size of the largest connected component that still contains infected nodes. This step helps us understand the impact of removing a specific node. For each removal, we record the size of this largest infected component and track which node results in the smallest size. If there are ties, meaning multiple nodes lead to the same minimized size, we resolve them by selecting the node with the smallest index. Finally, after evaluating all nodes, we output the node that, when removed, best minimizes the spread of malware. To deepen our understanding, here are some key insights. First, removing a node significantly impacts the graph structure and the connected components. By recalculating these components, we can gauge how the infection propagates after a node is removed. Second, the size of the largest infected component is directly tied to the spread of malware. The smaller this component, the more effective our solution. Finally, while this brute force approach involves exhaustively evaluating each node, it guarantees the optimal solution. However, to improve efficiency, we can reduce redundant calculations by reusing information about connected components where possible, which can make the algorithm faster in practice. To implement this algorithm effectively, we rely on a few key data structures. First, the adjacency list is crucial for representing the graph, especially when dealing with sparse graphs. It allows us to efficiently add or remove edges and iterate over a node's neighbors. Second, a visited array is used during DFS or BFS to track which nodes have already been processed, preventing redundant visits. Lastly, an infected set is helpful for quickly determining whether a node is infected. With this set, we can perform constant-time checks to see if a node belongs to the initially infected list, which is critical for efficiently measuring the spread of malware. Now, let's break down the key operations involved. DFS or BFS is used to traverse the graph and group nodes into connected components. The time complexity for each traversal is O, V plus E, where V is the number of nodes and E is the number of edges. Another key operation is edge removal. Removing a node requires us to remove all its edges, which has a complexity of O, D, where D is the degree of the node. Finally, for each connected component, we calculate the size of the infected portion. This involves iterating through the component and counting infected nodes, which takes O, V, time. These operations, when combined, form the backbone of our solution. Let's analyze the overall complexity of the brute force approach. For each infected node, we perform a graph traversal using DFS or BFS to recalculate the connected components. This results in a time complexity of O, K asterisk, V plus E, where K is the number of initially infected nodes. As for space complexity, representing the graph as an adjacency list requires O, V plus E, space. Additionally, we use a visited array and other auxiliary structures, which take up O, V, space. While this approach is computationally intensive, it ensures that we find the optimal solution by evaluating every possible removal. To tackle the problem, we start by importing the necessary modules like defaultIct and deque, which will help us manage the graph structure and perform breadth-first search efficiently. Then, within the solution class, we define the min-malware spread method, which accepts the graph and the list of initially infected nodes as inputs. First, we determine the size of the graph and convert the initial list of infected nodes into a set for quicker lookups. Next, we create a defaultIct called infected_by, which will map each node to the list of malware sources that can reach it. Now, we implement a helper function called BFS, or breadth-first search, to explore the graph. Starting from a given source node, this function uses a queue to traverse all reachable nodes. As we process each node, we skip those that are already visited or initially infected. For other nodes, we record the current source and their infected_by list. This ensures we track which nodes are infected by specific malware sources while avoiding duplicates or cycles. Finally, we iterate through each initially infected node and run BFS from it to populate the infected_by mapping. With the BFS results collected, we then calculate the unique contributions of each malware source. We initialize a contribution array to 0, where each index represents a node, and its value tracks the number of nodes exclusively infected by that malware. For each node in the infected_by mapping, we check if it is infected by exactly one source. If so, we increment the contribution for that particular source. After determining the contributions, we need to decide which node to remove to minimize the spread. The selection process prioritizes two criteria: first, the node with the highest unique contribution, and second, in case of ties, the node with the smallest index. To implement this, we initialize the best underscore node to the smallest index among the initially infected nodes and max underscore contribution to -1. As we iterate through each initially infected node, we update the best underscore node whenever we find a higher contribution or, in the case of a tie, a smaller index. Finally, we return the best underscore node as the optimal choice for removal. Here, we start by defining the min-malware spread method, which takes in a graph represented as an adjacency matrix and an array of initially infected nodes. The first step is to determine the size of the graph, n, and then convert the initial array into a set for quick lookups. This initial set helps us track which nodes are initially infected. Next, we create a map called infected by to store which nodes are infected by specific malware sources. Using this map, we can determine the nodes that are uniquely affected by each malware source. To populate this map, we perform a breadth-first search, or BFS, starting from each initially infected node. This BFS traversal identifies nodes that are exclusively infected by one malware source at a time. After the BFS, we calculate the unique contribution of each malware source by iterating through the infected by map and counting how many nodes are solely impacted by each source. This count is stored in the contribution array, which is indexed by the node number. Finally, we prepare to choose the best node to remove, which we'll determine based on the unique contributions. The next step is to decide which node to remove in order to minimize the spread of malware. We initialize max contribution to -1 and best node to the largest possible value. Then, we iterate through all the initially infected nodes. For each node, we compare its contribution to the current max contribution. If the contribution is higher, or if the contributions are equal but the node number is smaller, we update best node to the current node. This ensures that we select the node with the highest impact on reducing the spread, prioritizing smaller node numbers in case of ties. Once this loop concludes, the node to remove is stored in best node, and we return it as the result. After this, we define a helper method called BFS to handle the breadth-first search logic. In this method, we use a queue to traverse the graph and a visited set to keep track of the nodes we've already processed. We begin by adding the source node to the queue and processing nodes one by one. As we continue the BFS, we dequeue the next node to process and check if it has already been visited or if it's part of the initially infected set. If so, we skip it to avoid redundant processing. Otherwise, we mark it as visited and update the infected by map to indicate that this node has been infected by the current source. Then, we iterate over all the neighbors of the current node. If a neighbor is connected and hasn't been visited, we add it to the queue to process later. This ensures that we explore all reachable nodes in the graph while respecting the constraints of the problem. Once the BFS completes, the infected by map will contain the necessary information to determine how each node is affected by the initial sources. With this approach, we systematically identify the best node to remove and minimize the malware spread effectively. In this simple example, the graph has 3 nodes, represented by a connectivity matrix. Nodes 0 and 1 are initially infected. First, we initialize some variables. The size of the graph, n, is 3, the set of initially infected nodes, initial_set, is 0, 1, and infected_by is an empty dictionary that will later map nodes to the sources that infect them. Next, we perform breadth-first search, BFS, starting from each initially infected node. Starting with node 0, we initialize the BFS queue with node 0 itself and an empty set for visited nodes. However, as node 0 is part of the initial_set, it is skipped and no additional nodes are infected. Similarly, for node 1, the BFS queue starts with node 1, but since it is also in the initial_set, no unique infections are recorded. As a result, no nodes in the graph are uniquely infected by either source. With no unique infections recorded, the contribution array remains 0, 0, 0, indicating that none of the infected nodes contribute a unique infection to the graph. Now, to determine which node to remove, we evaluate the nodes in the initial list. For each node, we check its contribution to the spread of malware. Both nodes 0 and 1 have a contribution of 0. Since there is a tie, we select the node with the smallest index, which is 0. The result is to remove node 0, and the output is 0. Moving to another example, we now consider a graph where some nodes are exclusively infected by specific sources. In this second example, the graph has 4 nodes, and nodes 1 and 3 are initially infected. After initializing the variables, with n equals 4, initial underscore set equals 1, 3, and infected underscore by as an empty dictionary, we proceed with BFS starting from each node in the initial underscore set. For node 1, we start with a queue containing node 1 and an empty visited set. From node 1, we can visit nodes 0 and 2. As a result, nodes 0 and 2 are marked as infected by node 1, updating infected underscore by to 0, 1, 2, 1. Next, for node 3, we start with a queue containing node 3. From node 3, we visit node 2. Since node 2 is already infected by node 1, it is now marked as being infected by both nodes 1 and 3, resulting in infected underscore by equals 0, 1, 2, 1, 3. This tells us node 2 is infected by multiple sources, while node 0 is exclusively infected by node 1. After analyzing the infections, we calculate the unique contributions of each node. Node 1 uniquely infects node 0, so it has a contribution of 1. Node 3 does not uniquely infect any nodes, so its contribution is 0. This gives us a contribution array of 0, 1, 0, 0. To determine the best node to remove, we evaluate the nodes in the initial list. Node 1 has a contribution of 1, while node 3 has a contribution of 0. Since the goal is to minimize the spread of malware, we remove the node with the highest contribution. Here, node 1 is the best choice, and the output is 1. Now, we consider a third example to illustrate how tie-breaking by index works. In this final example, the graph has 3 nodes, and nodes 0 and 2 are initially infected. After initialization, with n equals 3, initial underscore set equals 0, 2, and infected underscore by as an empty dictionary, BFS is performed starting from each source. For node 0, we visit node 1 and mark it as infected by node 0, resulting in infected underscore by equals 1, 0. For node 2, we visit node 1 again. Since node 1 is already infected by node 0, it is now marked as being infected by both nodes 0 and 2, updating infected underscore by equals 1, 0, 2. This means no node is uniquely infected by either source. As a result, the contribution array is 0, 0, 0, indicating no unique contributions. To minimize the spread, we must choose the node with the smallest index from the initial list, as both nodes have equal contributions. Therefore, the node to remove is 0, and the output is 0. In this algorithm, we can break down the time complexity into 3 main steps. First, we have the BFS traversal. Here, for each node in the initial list, which we denote as k, we perform a BFS to explore the graph. The BFS operation, in the worst case, visits every node and edge in the graph. For a graph with n nodes and m edges, this takes n plus m time. Since we repeat this process for all k initially infected nodes, the total cost for BFS becomes k asterisk n plus m. Next, there's the processing of infection contributions. After completing the BFS, we iterate over all nodes and work with the infected underscore by dictionary. For each node, we check its list of sources, which in the worst case can involve up to k sources. This results in an n asterisk k time complexity for processing contributions. Finally, when selecting the best node to remove, we iterate through the initial list to find the node with the maximum contribution, which takes k time. These steps together cover the entire algorithm's workflow. When we combine these individual steps, the total time complexity becomes k asterisk n plus m plus n asterisk k plus k. Simplifying this further, we see that it can be expressed as k asterisk n plus m, as the term involving m typically dominates over k and n. Now, looking at the space complexity, we account for several key components. First, the graph is represented as an adjacency matrix, which requires n squared space. This is the most expensive component in terms of memory usage. Then, during the BFS, we use a visited set and a queue, each capable of storing up to n nodes in the worst case. However, since BFS is performed sequentially for each source node, this space does not scale with k. Another important component is the infected underscore by dictionary. In the worst case, each of the n nodes could be infected by all k sources, requiring n asterisk k space. These structures together contribute to the overall space usage. Additionally, we maintain a contribution array with n elements, which adds an n space requirement. When we combine all these components, the total space complexity becomes O, n squared plus n times k. Here, the adjacency matrix, with its O, n squared, space requirement, dominates the overall usage. To put this into perspective, consider the alternative of a naive brute force approach. In such an approach, we would remove each node in the initial list one by one and simulate the spread of malware to evaluate the impact. This would involve recalculating all infected nodes for each possible removal, leading to a time complexity of O, k*n squared, or worse, depending on the simulation method. In contrast, our current algorithm is more efficient. By using a single BFS for each source and leveraging the infected_by dictionary to compute contributions, we eliminate redundant computations and significantly optimize performance. Now, let's analyze the algorithm's performance in different scenarios. In the best case, where the graph is sparse with very few edges, the BFS traversal is efficient and takes O, n, time. This results in an overall time complexity of O, k*n. For the average case, where the graph is moderately connected, we observe a complexity of O, k*n plus m, balancing both nodes and edges. In the worst case, if the graph is dense with nearly the maximum number of edges, where m approaches n squared, the BFS operations dominate. Here, the time complexity becomes O, k*n squared. This scalability demonstrates the algorithm's efficiency compared to brute force methods, as it adapts well to varying graph densities and the number of initially infected nodes. Overall, the algorithm achieves a practical balance between time and space efficiency, even in challenging scenarios. When solving this problem, there are several common mistakes that candidates often make. First, not considering edge cases can lead to runtime errors or incorrect results. For instance, you might encounter graphs with no edges, graphs where all nodes are infected, or even a graph with just a single node. Ignoring these scenarios can cause your solution to fail during testing. Another frequent issue is inefficient component calculation. If you're recomputing the connected components from scratch every time you remove a node, you might end up with a time complexity of O, n squared, or worse, especially on dense graphs. This redundancy can significantly slow down your solution. Lastly, improper handling of multiple optimal solutions can also be problematic. If there are multiple nodes that result in the same reduction of infected nodes, the problem often specifies breaking ties by using the node index. Failing to account for this tie-breaking rule can result in incorrect answers, as it violates the constraints of the problem. These mistakes can be avoided with careful planning and attention to detail during implementation. Another area where candidates struggle is misunderstanding the graph representation. Graphs can be represented in different ways, such as adjacency matrices or adjacency lists, and confusing these formats can lead to implementation errors. For example, using the wrong representation might result in incorrect traversal logic or unnecessary complexity. Additionally, not optimizing for sparse graphs is another common oversight. Sparse graphs often allow for optimizations, such as using BFS or DFS directly, rather than relying on full matrix operations. Failing to leverage these optimizations can result in solutions that are unnecessarily slow or inefficient. By taking the time to understand the graph representation and tailoring your approach to the graph structure, you can improve both correctness and efficiency in your solution. Now, let's discuss some key insights for tackling this problem during interviews. One of the most important aspects is balancing brute force methods with optimization. Interviewers are often looking to see if you can identify redundant computations and eliminate them. Recognizing patterns is also crucial. This problem revolves around graph traversal, so techniques like union find, DFS, or BFS can be highly effective depending on the graph's size and structure. Another important strategy is clear communication. You should explain your assumptions explicitly and describe how you handle edge cases. For instance, make sure to articulate how you handle tie-breaking or optimize connected component calculations. Finally, when testing your solution, prioritize diverse test cases such as a fully connected graph, a graph with no edges, or a graph where all nodes are infected. This ensures your solution is robust and handles all edge cases correctly. This problem also connects to several related problems that are worth exploring to deepen your understanding of graph concepts. For example, LeetCode 947, most stones removed with same row or column, is a similar union find problem that involves managing connected components. Another example is LeetCode 990, satisfiability of equality equations, which also focuses on graph connectivity through union find techniques. LeetCode 261, graph valid tree, is another relevant problem, as it involves determining whether a graph is a valid tree by checking for connectivity and cycles. Finally, LeetCode 785 is graph bipartite, uses BFS or DFS for graph traversal, similar to the techniques you might use here. Studying these problems can help you recognize common patterns and refine your approach to solving graph-related challenges. When considering alternative approaches, there are a few strategies worth discussing. First, union find optimization can be a powerful tool. By using union find, you can dynamically maintain connected components as you remove nodes. However, this approach requires extra space and careful implementation to handle updates correctly. Another option is to use DFS or BFS traversal. Instead of recomputing all components from scratch, you can traverse the graph to assess the impact of removing a node. This method works particularly well for sparse graphs, though it may be less efficient for dense graphs. Finally, pre-computing all connected components at the start and updating them incrementally is another viable strategy. This reduces repetitive calculations but increases the complexity of handling dynamic updates. Each approach has its trade-offs, so the best choice depends on the specific properties of the graph and the constraints of the problem. Thanks for joining me in this problem-solving journey. We explored how to minimize malware spread by strategically removing infected nodes, discussed the importance of simulation in optimization problems, and highlighted key concepts like graph traversal. If you enjoyed this video, please like and subscribe for more algorithm tips and problem breakdowns. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!